Okay, you're right. Last lesson you had a look at circuit boards and what makes up a circuit board and the different components. Part of that was a conversation around how circuit boards carry an electronic current. And that current can essentially be used to carry data from one system to another. Today we're going to look at that in a little bit more detail and say, well, how can my data actually go in an electronic current? Interesting. Let's have a look. So, what are we learning and how do I know if I've got it? Well, our learning intention today is to understand what binary numbers are and how they fit into electronic circuits. So your success criteria, if you can define what binary numbers are and how data is sent around a circuit, so if you can tell me or just define what they are and tell me how they get sent around, success criteria number 1. Success criteria number 2 is about being able to convert between decimal and binary numbers, and we're just going to look at some basic conversions. So, like I said before, last lesson we talked about electronic circuits and their ability to be able to move data from one place to another. Now, the data that moves around a circuit is represented in an electric current, okay? So you'll notice that we were talking about, switches and gates being able to stop or temporarily hold a current. That data that's going around in the current, or that current that's going around your circuit board, is either on or off. So if I wanted to convert that into data, I can represent that with ones representing on and zeros representing off. And that's that's the basic foundation of data, ones and zeros. Now, those ones and zeros in levels up are used to represent other things, but at their most basic form, all data in our electronic current is represented with ones and zeros, or the current being on or off. The fancy names for these ones and zeros is binary, and sometimes some of you might have heard of the word binary. Binary is really the only thing, or the current's the only thing the electronic circuit really understands. Some of you may have heard the phrase that computers only understand ones and zeros, and this is exactly what that means. Binary numbers, or a binary digit, is either a 1 or a 0. Each binary digit is called a bit. Binary bits like to hang out in groups of 8. They're super big fans of hanging out in groups of 8. So each 1 or 0 is called a bit, and when they hang out together in a group of 8, it's called a byte. Okay, so if they're hanging out in groups of 8, how many different numbers can I store with a byte? Well, because there's 2 options, 1 or 0, I work on base 2. So we have here in the first 2 to the power of 0, which means I can only really store 1 in here. Whereas 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 32, 64, 128. So technically if I had a binary number of 1, 1, 1, 1, 1, 1, 1, 1, I could store 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So the biggest number that I can store with 8 bits is 255. Okay, 255. Now, if I wanted to represent, say, another number, say not just 255, let's get rid of this quickly. Say I wanted to represent another number, okay? Say I wanted to, with these 8 bits or a byte, I wanted to represent 8. How would I represent 8? Well, 8 would be represented by 0, 0, 0, 0, 1, 0, 0, 0. That's 8. If I wanted to represent another number, maybe I wanted to represent 12. Now I notice that 12 isn't a number, a whole number one, or 12 isn't represented by one of these whole numbers. So I'm going to actually have to make it up of a combination of these. Okay, so if I go from left to right, I go, well, does 128 go into 12? Nope. Does 64 go into 12? Nope. Does 32? Nope. Does 16? Nope. Does 8 go into 12? It sure does, which means I have 8, 12, 4 left over. So does 4 left over, and I'll just keep my running total down here. Does 4 go into 4? Sure does. 0, 0. So 12 is 0, 0, 0, 0, 1, 1, 0, 0. Okay, what about if I wanted to represent a trickier number? What happens if I wanted to represent, say, 39 in binary? Say I wanted to represent 39 in binary. Okay, let's give that a go. Probably need to rub a bit of this out just to give me a bit more working space. Here we go. Let's get 39. Okie dokie, 39 in binary. So does 128 go into 39? No, it doesn't. Does 64 go into 39? No, it doesn't. Does 32 go into 39? Yes, it does. How many do I have remaining? Well, I have 7 remaining. Cool. So does 16 go into 7? Nope. Does 8 go into 7? Nope. Does 4 go into 7? It sure does, which means I have 3 remaining. And does 2 go into 3? Yes, it does. 1 remaining and 1. So if I wanted to represent the number 39 in binary, it would be 0, 0, 1, 0, 0, 1, 1, 1. And that's it, guys. That's pretty much different numbers in binary. So, if my electronic circuit wanted to send the piece of data 12 from one place to another, what would it look like? I'm pretty sure that most of you should be hopefully able to get this one straight away without working. Does 128 go into 12? Nope. Does 64 go into 12? Nope. Does 32 go into 12? Nope. Does 16 go into 12? No. Does 8 go into 12? Yep, 4 remaining. 4, 0, 0. So the first thing that you need to do, no matter what happens when you're working out binary numbers, is you need to write this table down, guys. So in a moment, you're going to be asked to convert your own binary numbers. The first thing I'd like you to do on your paper when you're working it out is write 128, 64, 32, 16, 8, 4, 2, 1. Okay, and that's it, guys. That's binary numbers.